Hello and welcome back to hashtag W2F is SRE. I'm Jen Riggins. I'm going to be your co-host in this DevSecOps security track. Tim.
Hello, everyone. I need help. My hair's on fire. Really great to be here with you, Jen, on the DevSecOps track. Really looking forward to some amazing talks. As you know, it's a fire-themed conference. I think Holly Commons Dragon blew some fire on my head, hence the get up. But I'm really looking forward to the day. Really, really excited about it.
Okay. Yeah, we can't help. We hope y'all keep sharing your learning. Nothing's happening in isolation. We want to learn from you and our esteemed guests. So I'll let you introduce Tim.
Okay, so welcome to the DevSecOps track. And we've got our first speaker of the day, Andrew Martin, who will be talking about who's afraid of the big bad supply chain. Andrew?
Good afternoon. Thank you very much for having me.
It's great to have you. So off you go. All yours.
Much appreciated. Well, of course, in the thematic conflagration, fiery theme of the day, supply chains and CI/CD are typically burning in some way or another. So very happy to be here. Welcome. Reflections on supply chain trust, the software factory, aka who is afraid of the big bad supply chain. I'm Andy. I'm from a cloud native security consultancy called Control Plane, where we tackle difficult engineering and security problems. I've been very lucky to be involved with SANS and O'Reilly, HashiCorp and Docker. My background is development with the necessary security observation, and then of course operations as well, building up to the portmanteau of the track. I have again been very fortunate to collaborate with my esteemed co-author, Mr. Michael Hassenblas, on the book Hacking Kubernetes. It is available. It's actually now released, so apologies for the earliness inferred by this slide, like actually communicated. You can also go to the Control Plane website and download the first half of the book as a PDF behind an email wall. All feedback, always welcome. This is a view on breaking out of a pod, taking over a node, a cluster, a cloud account, and an organization from an attacker's perspective. And very pleased to have collaborated with my dear friend there. Okay, what will we do today? We will look at supply chains. They are in vogue, so hot right now. Then we'll just do a short demo on a simple supply chain attack. It is terrifyingly simple. We'll look at code signing and then artifact signing as a mechanism to at least build some tolerance and resilience to supply chain attacks from within the build system. And then finally, we get to the software factory, which is the new reimagination of CI/CD that we all know invariably so well. So much prior art, so many people really doing a lot of work in this space. At the bottom, we there see CNCF Tag Security, the technical advisory group. Please do come and contribute. If this is any of these things are of interest to you, we are working on reference implementations. We are taking cloud native projects and building reference CI/CD implementations for them. And we will progress more of that as we go through this talk. So what is a supply chain? Well, not only is it particularly in vogue, it's also anything that we depend upon. So from a military context, it is every single nut, bolt, and piece of metal that goes into an aircraft carrier, for example. Each of those have their own SKU, their software, their stock keeping unit in physical terms. So when we build an aircraft carrier on a day-to-day basis, perhaps not, every single item, every single piece of that aircraft carrier comes from a known and trusted source. Pharmaceuticals, of course, this is very important when humans are ingesting things. The same for food, manufacturing, and finally software. Everything has a supply chain, and we'll look at exactly why that's such a terrifying prospect, because it relies on trust. We have a producer and a consumer. The producer generates something and passes it to a consumer. The consumer implicitly trusts that thing. And we'll look at exactly what trust means and how we can amplify or at least augment some of it. And yes, the Wicked Witch of the West finds this, I don't think she is, but nevertheless, the evil stepmother finds this particularly amusing. So in software terms, any code that ends up running in production has a supply chain component to it. This this GIF has loaded and looped at the wrong end. What could possibly happen here, I hear you ask? This is a potential supply chain problem. There we go. No individuals or robots were hurt in the making of this GIF. Okay, so from a software supply chain perspective, everything is now software. This is how we model our systems. Our applications are defined as code, but so is our infrastructure. By extension, security and policy, these things are now well defined. The boundaries are blurring on the job roles. If we define everything as software, then we can apply standardized testing to some of these things. So especially static analysis, composition scanning. Are my dependencies safe? Have I got correctly formatted for whichever language, maybe Python or YAML? Have I introduced a potential vulnerability, maybe something language specific like semgrep? So we see everything as software. Everything then also has a supply chain and needs to be built. There are plenty of types of pipeline. Just very briefly, we can build applications, infrastructure, of course, but our testing for security, side effects, misconfigurations of cloud infrastructure, these are how organizations get breached in the modern cloud era. So our software is composed of other people's software, and we rely upon them. In this instance, if the intermediary, Bob, is able to drop malware into the thing that is being passed on, maybe that's an application library, maybe that's some closed source vendor software, we're then running malware in production. This is the attacker's goal, of course. So we have a huge, extensive level of transitive trust. Here we can see a deployed system is the ultimate goal. That system must trust the repository that the application that is about to be deployed rests in, the build system where it is compiled or packaged, the transit between the build and the application repository, and finally, and perhaps most terrifyingly, open source. We love open source. It brings us huge advantage, but it also is somewhat of an unregulated Wild West. We must also trust the build tools that do the compilation. This is a 22-year-old problem at this stage. Reflections on Trusting Trust is the seminal work on malware within compilers. So we have this opportunity as an attacker to infect a compiler, and then the compiler will generate supposedly legitimate binaries with malware or an implant or a backdoor inserted into it. And this is the seminal work. Okay, so how do we exercise this smashing supply chain attack? Well, first of all, we're going to take a view from Dread Pirate Captain Hashjack. He is the anti-hero of the Hacking Kubernetes book, and we model him as a state-sponsored adversary in order to generate a threat model, in order to understand what problems potentially he could bring. So what problems have we seen recently? Well, we had the Revil ransomware gang. They shut down the Colonial Pipeline on the east coast of the United States. That caused extreme transit and logistical issues as a large number of tankers had to then drive fuel down the east coast of the US to the various places that the pipeline landed, just because Revil managed to drop crypto locking software via a trusted supplier of the Colonial Pipeline management company. we saw Okta recently subject to the same problem. We've seen that the MageCart group attack British Airways and various other organizations in this way. If we outsource something to a help desk firm, for example, and they're breached, well, then probably our organization is also breached because they're part of our supply chain and they have an inherent trust. We also saw SolarWinds. I'm sure everybody remembers, and it doesn't bear too much more repeating, but this was build tampering. Then we have some other less well-known ones, co-covered in Homebrew. All of these have had some form of upstream attack where something that they consume has been compromised, and they consequently, these products all suffered a compromise. Thanks again to Tag Security, one of my favorite places to be. We maintain a catalog of supply chain compromises, so one can have a look back and see what has gone wrong, look for patterns and trends, and take a relatively detailed overview from each of the individual attacks. So what might we do to attack a supply chain? Well, we might get into the source codes, we might go upstream to a trusted supplier, or we could impact the runtime environment, either on the build server or in production, to some extent on the developer's machine as well, slightly different to the source code. We have a open source framework called SLSA. SLSA is still very much in development. It is a collaborative exercise between some of the major cloud players and financial institutions. SLSA tries to give us a framework by which to reason about the risk and, by extension, the security of our build infrastructure. As you can see here, lots of things can go wrong. We will do a demo of B, he says, thinking more carefully. Actually, we may even do, we'll do a demo of attacking an open source package, but it's not exactly covered on here. It's actually slightly to the left of developer. It took me a moment to reparse that. So here is our demo. What we'll do here is model a compromised NPM package. So an EUD is an end user device. We will play the part of the developer, trying to install a package from NPM that is malicious in some way. And then that package installer will run malware that then executes on my system with my privileges because I'm the user that's run the installation. And what do I have access to in my home directory? We will see very briefly. Okay, so what do we have here? This is a malicious NPM package. It is called supply chain NPM. Unsurprisingly, let's have a look at the, let's run the demo. Have a look at the package. Okay, so what have we done here? This is the manifest that goes with the package. And we can see we've got some tests. So NPM tests, great. Yeah, we can just run that code. What about pre-install? Well, pre-install is an NPM script option that executes that script in a subshell or whatever code you pass to it at installation time. This is running with the privileges of the current user, in this case me, and I'm sure it doesn't take too much intuition to guess what's about to happen when I do an NPM install. So this is a local install because I'm not permitted to push malicious code to NPM, as indeed nobody should be. So for the purposes of example, let's install this package. What happens? We're running somebody else's code. What did we see there? First of all, we can install a command and control endpoint if we wanted to. We can also install a keylogger. If we have passwords on the contents of our SSH directory or our GPG directory, then these things will then be discovered and unlocked by a keylogger. And then, of course, we can just grab other things like AWS information, keys potentially, even with 2FA on authentication into our cloud accounts. If we're using OAuth, then a session token is dropped into our home directory owned by our user. If somebody can exfiltrate that, they have maybe an hour's worth of tampering or reconciling and persisting their position, maybe they would look to create another account that then that they can generate their own credentials for. What's the point here? Don't install things without looking at them. Does everybody check their dependencies before installing? Absolutely not. What's the problem? Too much trust, inherent trust in everything. But there are some solutions to this, at least partial solutions. 2FA is important. It means that that attack goes from just stealing key material to key material plus keylogger, and maybe some temporal and sort of time-bound things. Avoid plain text credentials because they can be easily stolen. Crypto wallets. Most of the attacks we've seen in this space so far have been looking for hot wallets. Those shouldn't really be a thing. I'm sure we agree. And then finally, air gapping our development environment, which generally is probably impractical. Okay, so into our build infrastructure. Do we trust our build machines? Ideally so, but potentially not. So what is attestation in this context? It is the process of building a thing, generating metadata about it, and then finally verifying that metadata, that provenance, is correct at deployment time. This gives us an end-to-end story where we hope that things have not been tampered with. The difficulty here, of course, is if the build infrastructure is compromised, these attestations, to coin a phrase, crap in, crap out. If we're going to sign something that's already compromised, we have no effective security guarantees. We just know that it was given to us and it remains compromised. There are plenty of useful demos in this space, some from Supply Chain Security Con at KubeCon North America. We are also running Supply Chain Security Con at KubeCon Europe in Valencia in only a few weeks, actually. So, yep, there's a 2-day security con. Please do join if security is of interest to you, especially in a cloud-native manner. And what we see in this particular demo from Mr. Michael Lieberman is a look at Canico, which is Google's container image builder, and Tekon chains, and then using Caverno as an admission controller in Kubernetes, deep packet inspection for a request to say, is this signed? Did it come from the build server? And if not, this is rejected and will not be permitted to deploy. Okay, so what is signing then? What is this thing that we're using in order to prevent tampering? We begin with some data, some amorphous, anonymous blob. It doesn't matter what the data is. In our case, a container image or tarball or collection of files. We then take a private key and we use that private key to generate a signature. That signature is cryptographically anchored to the data with a hash of the data's contents. So we then have a signature that is relevant only to that blob of data. If one bit of that data changes, the hash changes, and the signature is invalid. It doesn't match the hash, so it can't be used to validate that new piece of data. And then we use that signature alongside the data in order to verify the data has not changed. We can use in Toto. This is one of the foundational technologies in Tekton chains. It gives us intermediate build stage signing. So we check out the code, we sign it, and we make sure that when we go to the test stage, the output of the previous stage is the same as the input to the next stage. This fundamentally is a chain of signatures. This is helping to defeat supply chain tampering. Importantly, if somebody is able to get into the build step itself and perform some manipulation of the build, the mutation in each stage will get signed. So this is not full infallibility for a supply chain, but it gets us into a much better place for passing data between build stages. Here we have the materials and products, and we can see we have to define what will happen in the build, and then in Toto we'll observe the inputs and outputs, validate their contents with those signatures, and pass or fail based upon whether the thing matches the expected signature. Okay, we can also do this with container images. As you can see, we can sign the entire SHA of the container image. There are also SHA-256 layers within the image, and those can be individually signed. So there's a combination of different approaches that we can use here. We see some work from the SigStore group, Recore, which is a public transparency log. So imagine our certificate transparency. This was introduced a few years ago to defeat rogue CAs or stolen roots of trust. So somebody, for example, gets into a VeriSign or a DigiCert, steals the root signing key and starts to generate their own certificates. Well, every certificate has to be pushed into this global certificate transparency log, and that gives us somewhere that we can then observe certificate generation. And if somebody is generating certificates with our root of trust that is not us, well, that's a red flag. Let's rotate all of our credentials. Let's rotate all of our private keys because we've been breached. By mandating this and verifying it in browsers, we dramatically increase the security of the global root CA and signing systems. Recore looks to do this for application packages. So we release an application version 1.1, we sign, we push that signature to Recore, and then when somebody comes to consume that package, they can validate that the package they've downloaded is the same package that I uploaded by checking the signature on Recore. Really analogous to those certificate transparency logs. Notary v2 will also enter the space. SigStore has some other bits and bobs in here, including a root of trust of its own, the Folkio certificate authority that we see there. But a quote here from Mr. Michael Lieberman again. This is about trusting people. Software does not compromise itself. Love that quote. Everything, trust the internet, it's all based on interpersonal relationships, trust levels, communication. What we're doing here is validating that the person that we trust, that we believe acts in good faith and has good intentions, is the person who gave us the software artifact that we're looking for. We also have an extra concept to throw in here, which is SPIFFY, the secure production infrastructure for everybody. This gives us a workload identity. If you are at KubeCon, my esteemed colleague, Mr. Richard Featherstone, is doing a talk on workload identity and where SPIFFY fits into that. Ultimately, the point here is that we can generate ephemeral credentials as part of the root of trust for signing, so that even if we do have compromised build infrastructure and those credentials are stolen, they can only be used outside the build for a very short period of time, maybe 45 minutes or whatever the SPIFFY certificate expiry is set to. There's a lot more complexity in this, but as a call out, I love this project and it continues to go from strength to strength. Some of this code has been merged now. We now have in toto working with SPIFFY Inspire, and big thanks to the Boxboat guys for shipping those features. Okay, finally onto the software factory. We're building pipelines for other build pipelines. This means we're running CI/CD for everything, including CI/CD itself, ultimately. This is aggressive automation. This is our DevOps part of the DevSecOps, and it welcomes all signing approaches. We can build everything in a software factory, from our infrastructure through to the platforms that we're actually generating. And by that, I mean another piece of build infrastructure, potentially. Applications, data, yes, the whole shebang. The Department of Defense has a reference design for this. Ultimately, the goal here is to be able to reproduce the entire software factory end-to-end using itself or using another software factory. It's a recursive build mechanism that guarantees we don't end up with snowflake Jenkins instances running our entire organization. There is a reference architecture, as we've mentioned. There's a slightly deeper view in here. What we have at the bottom is the identity attester. So this is a trusted process that is handing out identities, workload identities to jobs. We can base those workload identities in any trusted, unique thing about the workload. Kubernetes gives us a service account. AWS gives us a resource identifier for our VMs, for example. We can anchor this in a TPM or a trusted execution environment to use a cryptographic signature rooted in hardware. And again, there's some exciting projects coming out in this space. So what we're looking at here is potentially end-to-end hardware to application to production, signing and validation of everything that we run. A slightly closer view here, we've got Sigstore and Rekor in Tekon chains. Tag Security has a reference software supply chain architecture that includes some of these projects. Again, I welcome anybody who'd like to talk further about that or get involved. We are an open group. And then finally, the reason that supply chains became so hot, let's say, and fiery in the last year or two is SolarWinds. SolarWinds was compromised by a foreign intelligence service. An implant was dropped into their trusted server agent, and that server agent was then installed by Microsoft and the Department of Defense and hundreds of other incredibly sensitive and classified organizations. This was because the build infrastructure was compromised. In order to defeat the compromise of the build infrastructure, SolarWinds redesigned their build and release process. They now run parallel pipelines. So if somebody compromises pipeline A, the reproducible artifacts created by pipelines A and B will not match. Those hashes, the signatures, they will be different. This means we assume that we have a compromise at some point. Of course, this is not infallible. If somebody is able to compromise a shared piece of code between the two or compromises Tekton, the application itself, this does not defeat those attacks. But this is the distributed build style that Debian and Arch and various other reproducibility-focused, Nix, of course, reproducibility-focused build Linux distribution build environments have been using for a number of years. It's a good look, and it does certainly make us more secure. There is a tag security. This is Sigstore. There is a white paper here from some of the authors of Tekton and the cosign and Rekor technologies, detailing a look on zero trust supply chains that is well worth a read. And with that whistle-stop tour of the various components of a software factory, thank you very much. I appreciate your attention and have a wonderful rest of the day.
Cool, awesome. Thanks, Andy. A lot to digest there, a lot of information. I'll definitely rewatch this over and over again because I'm a security buff, pretty much like you. I keep on shouting. We need it more secure. We need it more secure. I like your quote, don't install things without looking. And just before I said I'm a security buff, yeah, I've done that. I think we all have installed stuff. Yeah, I'll trust that .sh file and simply run it. And what kicked into mind was also the XKCD image of how a software is built, and then there's one little bit of open source software which is being trusted to ensure that everything's running smoothly. And if somebody decides just to poke it a little bit, put in a bit of vulnerability into it, it affects the whole supply chain, as you said.
Yes.
So how do you? So you said it's all about trust. Which is interesting. You do have to trust somebody at a point in time. Where do you start? Where do you go? How do you decide where to trust?
Amusingly, that XKCD, perhaps unintentionally, I think it refers to a maintainer in Nebraska. That maintainer actually exists, and they maintain Alpine Linux, And amusingly, as I say, perhaps accidentally, that does represent a real situation, almost unbelievably. Yes, the roots of trust that we must trust, unfortunately, and a lot of work is being done to untangle these, are things like hardware manufacturers. We run firmware microcode on our CPUs. Those of you that are aware of the Intel management engine vulnerabilities may not be able to sleep at night. Remote code execution on a CPU across the network, insane that that's ever been permissible, but we must trust our hardware. We must also trust our operating system vendors. They ship the list of root CAs, the public keys of those certificate authorities that our browser trusts. We also have to trust our browser manufacturers. That is a deep Google, Microsoft, and Mozilla generally trust for most of us. To some extent, we then have to extend that, and those are kind of fundamental backdoors. We can't escape those. We have to use those. Then we've got more optionality when it comes to which applications we install. Again, as a user, we keep key material that references our privilege in our home directory. And so anything that we install from the internet that can read the home directory potentially can compromise our identity. That then becomes the applications that we install, their dependencies, the transitive dependencies. As software developers, it's anything that we use for local build environments. This really is why containers have such a dramatic uptick in local build safety, because you can only access parts of the file system that are mounted into the container. So you can install potentially hostile things that not necessarily so hostile that they'll attack the kernel, which is potentially a risk, of course. We see things like dirty pipe and net filter vulnerabilities that allow kernel breakouts from containers, container breakouts by the kernel. But yes, that trust relationship is wide, expansive. We don't pipe to bash, but we also don't read the source code of the things that we install. It's not a great situation. Signing gives us one little extra step up of trust, but ultimately it's a little bit of a Wild West. And over the course of the next year or two, I expect this to regain a lot of industry focus, as obviously it has begun to.
Yeah, I think, yeah, as you said, signing is extremely important. And even more powerful when you even start signing your Git commits, for example.
Big fan. Yeah.
That the person who's pushing the code is trusted within the organization. I think that's it for us. We've got a small thanks again, Andy. Really good talk, and a lot of information, as I said, to digest. I'll be posting your talk to everybody I know. It's like, look at so thanks a lot. To the rest of I'm sure Andy will still. Are you still staying on? Can you chat?
Yes.
There will be. If you do have any questions for Andy, go to the chat and do ask those questions. He'll be around. In the meantime, we have about a 15-minute break, and do come back on the DevSecOps track for our next speaker, Mario, who will be talking of why GRC needs SRE. Too many acronyms there for me. Thanks a lot.